The ideal gas law is called as much because it relies on and is based on a conceptual model of a gas that's highly idealized. The assumptions that are built into the ideal gas model are captured in the kinetic molecular theory of gases, which we'll talk about in this video. One thing to notice about the ideal gas law, PV equals nRT, is that there is no mention of the identity of the gas in the derivation of the ideal gas law or in any of the variables, for that matter. There's nothing that depends on molecular structure built into the ideal gas law. In fact, we'll see later that gas laws for real gases do in fact have parameters that depend on molecular structure. But for the ideal gas law, there's no mention of the identity of the gas, and so the ideal gas law holds in theory for any gas. Now, some gases are more consistent with the ideal gas law than others, and their consistency depends on their agreement with the assumptions of the kinetic molecular theory. So the ideal gas law holds only when the assumptions of the kinetic molecular theory of gases are met. And those assumptions are the following. First of all, gas particles do not experience intermolecular forces or interact with one another in any way except instantaneously during collisions. What that means essentially is that the gas particles are so far from one another in an ideal gas that any sort of interparticle forces, for example repulsion between electrons in two molecules, is essentially nil because the distances between particles are so large. The second assumption is that gas particles take up zero volume. Every particle has access to the entire volume of the container at all times. If this were not true, then we could imagine that the volume accessible to the gas particles would depend on the volume of an individual particle, right? And then we're bringing in the identity of that specific gas. So the ideal gas model, the kinetic molecular theory, assumes that gas particles take up zero volume, so that every single molecule has access to the entire volume V of the container. Assumption 3 is that collisions between particles are perfectly elastic and dissipate no energy. The kinetic energy before a collision is equal to the kinetic energy after a collision, and kind of by extension, gas particles have only kinetic energy. So for example, when two particles collide with each other, they can't transfer their kinetic energy into a different form of energy. A collision between gas molecules can't excite an electron to a higher energy level, for example. Now, of course, we know in real life and practice that that's untrue, but again, given the scale of collisions and the scale of a gas, this assumption holds up pretty well in the context of measurements of gases. The fourth assumption is that gas particles move according to Newton's laws of motion. That means that a particle that does not collide with anything moves with a constant velocity v until it collides with a wall or another particle, at which point the laws of collision can be derived directly from Newton's laws of motion. So these are the four big assumptions. And we've already alluded to the fact that all real gases, to some degree or another, violate one or more of these four assumptions. And so it's interesting that in spite of the fact that all gases to some degree violate these assumptions, the ideal gas law is still quite good at predicting the properties of a variety of gases. Before leaving this video, I wanted to talk a little bit about our motivations for understanding the kinetic molecular theory. It's used in chemical thermodynamics, theories of solutions, chemical reactions, and all kinds of areas throughout chemistry. And in fact, we will see it again in discussions of thermodynamics. The problem with taking into account interactions between particles is that there are a huge number of particles in a typical gas. So, for example, if we wanted to keep track of interactions between particles, we'd need to know the positions of all the particles within the gas, so that we could calculate, for example, electrostatic repulsion using Coulomb's law between each pair of particles in the gas. For a mole of gas, that's 3 times 6.02 times 10 to the 23rd position coordinates to keep track of. Simply impossible, even for the most powerful of supercomputers, to be able to do that. Even for the simplest of gases, a mole of gas is simply too many particles. One of our historical solutions to this problem has simply been to throw out the idea that particles interact with each other. And it is true, and the proof is in the pudding in the sense that the ideal gas law works well, that in many cases interparticle forces are weak or negligible, or in the course of a process they don't change much, and so we can neglect their contribution to the nature of a process. In cases like this, they can be ignored, and this is built into the first and third assumptions of the kinetic molecular theory. So anywhere where we want to ignore intermolecular or interparticle forces, the kinetic molecular theory and the ideal gas model can be valuable.